Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will do the circuit analysis using the Laplace transform. So in the previous video, we have seen that how to find the Laplace transform and the inverse Laplace transform. So now with the help of it, now let us see how to do the circuit analysis. So as a first step, we will transform the given electrical circuit into the S domain. That means we will find the equivalent Laplace domain representation for the each circuit element. And after that, using the different circuit analysis techniques like the nodal or the mesh analysis, we will find the voltages and the current in the circuit in the S domain. Now while finding these voltages and the currents, we can even use the other circuit analysis techniques like the source transformation and the superposition theorem. So once we get the equation of the current and voltage in the S domain, then using the inverse Laplace transform, we will find the equivalent time domain expressions for these currents and the voltage. So in this way, using the Laplace transform, we can do the circuit analysis, and by following these steps, we can find the voltage or current across the any circuit element in the time domain. So first of all, let us see how to represent the basic circuit elements like the resistor, capacitor and the inductor in the S domain. So once we know that, then we can easily represent any circuit in the S domain. So first, let us see how to represent the resistor in the S domain. So let's say the voltage across the resistor is equal to V of t. And because of this voltage, let's say some current I of t is flowing through the resistor. So as per the Ohm's law, we can say that this voltage V of t is equal to I of t times R. So after taking the Laplace transform, let's say the voltage and the current in the S domain is equal to Vs and the Is. And since the R is constant, so it will remain same in the S domain. So after taking the Laplace transform, we can say that this voltage V of S is equal to I of S times R. Or in other words, this R is equal to V of S divided by I of S. That means for the resistor, the equivalent S domain circuit is same as the time domain circuit. Similarly, let us see the equivalent S domain representation for the inductor. So let's say the voltage across the inductor is equal to V of t and the current through the inductor is equal to I of t. Now we know that the voltage across the inductor can be given as L times this di divided by dt. So now let us take the Laplace transform of this equation. So after taking the Laplace transform, let's say the voltage and the current are V of S and the I of S. And using the differentiation property of the Laplace transform, this di divided by dt can be written as this S times I of S minus I of 0, where this I of 0 minus is the current through the inductor at time t is equal to 0 minus. That means this V of S is equal to Ls times I of S minus L times I0 minus. So based on the given expression, this is the equivalent S domain circuit for the inductor, where this Ls represents the inductance and this L times I0 is the voltage due to the initial current. So we can say that this is the equivalent S domain circuit for the inductor. Now using the source transformation, this voltage source can also be represented as the current source. So now in this expression, let us bring this term on the right hand side. And now if we divide both sides by the Ls, then this current I of S can be written as this V of S divided by Ls plus I0 minus divided by S. And this is the equivalent circuit representation for the given expression, where this I of S is the incoming current to the inductor and this V of S is the voltage across the inductor. That means if I0 minus is the initial current through the inductor, then these are the equivalent S domain representations for the inductor. So as per your convenience, you can remember any one of these two representations. And using the source transformation, it is possible to derive the other one. So while solving the examples, based on the given circuit, we can use any one of the representation. Now in these representations, we have assumed that there is an initial current through the inductor, and we have denoted as the I0 minus. But if the initial conditions are 0, or in other words, if this I0 minus is equal to 0, then in the S domain circuits, this voltage and current source will become 0. That means when the initial conditions are 0, then the equivalent S domain representation for the inductor is equal to Ls. So similarly, now let us see the equivalent S domain representation for the capacitor. So let's say the voltage across the capacitor is equal to V of t, and because of that, the current through the capacitor is equal to I of t. So we know that the current through the capacitor can be given as C times dV divided by dt. So now let us take the Laplace transform of this expression. So after taking the Laplace transform, let's say the current and the voltage are Is and the Vs respectively. And using the differentiation property of the Laplace transform, this dV by dt can be written as this S times Vs minus V of 0, where this V of 0 minus is the initial voltage across the capacitor at time t is equal to 0 minus. So further we can write this expression as this Cs times V of S minus C times V of 0. And based on this expression, this is the equivalent circuit. So as you can see, this I of S is the incoming current to the capacitor, and this V of S is the voltage across the capacitor. And as you can see, this 1 over Cs is the impedance of this capacitor. And this current source exists because of the initial voltage across the capacitor. So this is the equivalent S domain circuit representation for the capacitor. Now using the source transformation, this current source can also be represented as the voltage source. So using the source transformation, if we convert this current source into the voltage source, then it will come in series with this capacitor, and its value will be equal to this 1 divided by Cv times this C times V0 minus, or that is equal to this V0 minus divided by S. And since this current source is going upwards, so the positive terminal of the voltage source will be on the top side, while the negative terminal will be on the bottom side. So this is the equivalent S domain circuit representation for the capacitor. But suppose if you do not know the source transformation, then from this equation also we can get the same circuit. So if we bring this term on the right hand side, then this is how we can write it. And now let us divide both sides by the Cs. That means now this voltage V of S is equal to Is divided by Cs plus V0 divided by S, where this 1 divided by Cs is the impedance of the capacitor. So based on this expression, this is the equivalent S domain representation for the capacitor. That means these are the two equivalent S domain circuit representations for the capacitor. So according to your convenience, you can remember any one of them, and using the source transformation, it is always possible to find the other one. So like I said earlier, during the circuit analysis, depending on the given circuit, we will use any one of the following representations for the capacitor. That means these are the equivalent S domain circuit representation for the capacitor whenever there is an initial voltage across the capacitor. But suppose if the initial conditions are 0, or this V0 minus is equal to 0, in that case this current and the voltage source will become 0. And in that case, the equivalent S domain representation for the capacitor is equal to 1 divided by Cs. So in this way, we found the equivalent S domain circuit representation for the inductor, capacitor and the resistor. So now, let us take the couple of examples, and through that, let us understand how to do the circuit analysis using the Laplace transform. So in the first example, we have been given this circuit, and we have been asked to find this output voltage across the inductor. And here, we have been given that the initial conditions of the circuit are 0. That means there is no initial current or the voltage across the any element. So as you can see over here, the voltage to the circuit is the unit step function. That means before the time t is equal to 0, the value of this voltage source is equal to 0. And at time t is equal to 0 plus, it will provide a 1 volt of constant voltage to the circuit. So first of all, let us find the equivalent circuit in the S domain. So earlier, we have already seen that how to represent the basic circuit elements in the S domain. But here, since the initial conditions are 0, so we can say that the equivalent S domain representation for the inductor will be equal to Ls. Similarly, the equivalent S domain representation for the capacitor will be equal to 1 divided by Cs. And for the resistor, that is equal to R. So here, in the equivalent S domain circuit, this 1 ohm and the 5 ohm resistors will remain as it is. While for this capacitor, the equivalent representation is equal to 1 divided by Cs. And here, since the value of C is equal to 1 by 3 Faraday, so we can say that that is equal to 3 by S. Similarly, for the inductor, the equivalent representation is equal to Ls. And here, since the value of L is equal to 1 Henry, so we can say that the equivalent representation is equal to S. And like I said earlier, here the input is the unit step voltage. That means for the t greater than or equal to 0, this input is equal to 1, and for the t less than 0, its value is equal to 0. So now we know that the Laplace transform of this unit step function is equal to 1 divided by S. So in this way, we got the equivalent S domain representation for the each circuit element. And based on this is the equivalent circuit in the S domain. So now, what we will do, using the mesh analysis, we will find the current in both the loops, and using those currents, we will find the output voltage V of S across the inductor. So let's say the current in both the loops are I1S and the I2S respectively. But here, during the mesh analysis, for our simplicity, we will represent these two currents as only I1 and I2. So now, if we apply the KVL in the first loop, then we can write it as this 1 divided by S, that is equal to this 1 times I1 plus 3 by S times this I1 minus I2. Or in other words, this 1 divided by S, that is equal to this 1 plus 3 divided by S times I1 minus 3 divided by S times I2. So let's say this is our equation number 1. Similarly, now let us apply the KVL in the second loop. So applying the KVL, we can write this 5 times I2 plus S times I2 plus 3 divided by S times this I2 minus I1, and that is equal to 0. Or further we can write it as minus 3 divided by S times I1 plus 5 plus this S plus this 3 divided by S times I2, and that is equal to 0. Or from this, further we can write it as this I1 is equal to this S divided by 3 times this 5 plus S plus this 3 divided by S times I2, or that is equal to this 1 by 3 times this S square plus 5S plus 3 times I2. So let's say this is the equation number 2. So now we can put this value of current I1 in the first expression. And by putting that, let us get the expression for the current I2. So now in this expression, if you put the value of this current I1, then further we can write it as is 1 divided by S, that is equal to this 1 plus 3 divided by S times this 1 by 3 times this S square plus 5S plus 3 times I2 minus 3 divided by S times I2. So now if we multiply both sides by the 3S, then we can write it as this 3 is equal to this S plus 3 times S square plus this 5S plus 3 times I2 minus 9 times I2, or that is equal to S cube plus 5S square plus 3S plus 3S square plus 15S plus 9. And over here we will also have this minus 9. So we can say that this 3 is equal to this entire term times I2. So here this 9 will get cancelled out, and if we further simplify it, then we can say that this current I2 is equal to 3 divided by this S cube plus this 8S square plus 18S. So in this way we found the expression of this current I2, and we know that this output voltage V out is equal to S times I2. That means this V out is equal to this S times I2, and that is equal to this 3 divided by this S square plus 8S plus 18. So now we can further write this expression as this 3 divided by this S square plus 8S plus 16 plus 2. And we know that this S square plus 8S plus 16 is equal to s plus 4 whole square. So we can say that this v of s is equal to 3 divided by this s plus 4 whole square plus 2. And this 2 can be written as this root 2 whole square. So further we can write it as this 1 divided by root 2 times this 3 times root 2 divided by this s plus 4 whole square plus root 2 square. So we know that the Laplace transform of the sin omega t is equal to omega divided by this s square plus omega square. That means here this omega is equal to root 2. That means now if we take the inverse Laplace transform of this term, then we will get the expression in terms of the sine term, where the omega will be equal to root 2. And using the frequency shifting property, further we can say that that is equal to this e to the power minus 40 times this sine root 2t. And here we will also have this 3 divided by root 2. That means the v of t is equal to 3 divided by root 2 times this e to the power minus 40 times the sine of root 2t. So in this way, using the Laplace transform, we found the voltage across this inductor. Now without this Laplace transform, if we had gone for the direct circuit analysis, then it would have been little difficult. But as you can see, with the help of the Laplace transform, we can easily do the circuit analysis for this kind of circuits. So now, let us take another example. So in this example, we have been given this circuit and we have been asked to find the voltage across this 4 ohm resistor. And here, once again, the initial conditions in the circuit are 0. So to find this output voltage, first let us find the equivalent circuit in the S domain. So here, since the initial conditions in the circuit are 0, so we can say that the equivalent circuit for this capacitor will be equal to 1 divided by Cs. And here, since the C is equal to 1 by 4 Faraday, so we can say that that is equivalent to this 4 divided by S. Similarly, the equivalent S domain representation for the inductor will be equal to Ls. And here, since the L is equal to 1 Henry, so that is equivalent to S. And for the resistor, it will remain as it is, that is equal to 4 ohm. And now, if we see this current source, then that is equal to 10 times u of t. That is a step function with the amplitude of 10 ampere. So if we take its Laplace transform, then that is equal to 10 divided by S. So in this way, we got the equivalent S domain representation for the each circuit element. So we can say that this is the equivalent S domain circuit for the given circuit. So here, to find the output voltage Vout, we have two options. The one is, either we can use the nodal analysis and we can find this node voltage. And from that, we can easily find this V of S. And the second option is, using the source transformation, we can convert this current source into the voltage source. And then after, by applying the KVL, we can easily find this output voltage. So here, we will use the second approach. So first, using the source transformation, let us convert this current source into the voltage source. So as you know, in the source transformation, when we convert this current source into the voltage source, then this impedance will get multiplied with the current source. So in this case, that is equal to 4 by S times 10 by S, or that is equivalent to this 40 divided by S square. That means this is the equivalent voltage source. And since the current is flowing upwards, so the positive terminal of the voltage source will be at the top side, while the negative terminal will be at the bottom side. And this impedance will come in series with this voltage source. So this is the equivalent circuit after the source transformation. And now, by applying the KVL equation in this loop, we can easily find this output voltage. So let's say the current in the loop is equal to I of S. So applying the KVL in the loop, we can say that this 40 divided by S square, that is equal to this 4 by S plus this 4 times this current I of S. Or we can say that this current I of S is equal to 40 divided by S square divided by 4 by S plus 4. So if we further simplify it, then we can write it as this 40 divided by this S times this S square plus 4S plus 4. That means this current I of S is equal to 40 divided by this S times this S square plus 4S plus 4. And we know that this output voltage V out is equal to 4 times I of S. So that is equal to this 4 times this 40 divided by this S times this S square plus 4S plus 4. Or we can say that this output voltage V of S is equal to 160 divided by this S times this S square plus 4S plus 4. Now we know that this S square plus 4S plus 4 is equal to S plus 2 whole square. So in this way, we got the expression of this output voltage V of S in the S domain. So now, if we take the inverse Laplace transform of this term, then we will get the time domain expression of the output voltage. And to find this inverse Laplace transform, here we will use the partial fraction expansion method. So in the previous video, we have already seen that how using the partial fraction expansion method, we can easily find the inverse Laplace transform. So here, using the partial fraction expansion, we can write this expression as a divided by s plus b divided by s plus 2 plus c divided by s plus 2 whole square. And using the residue method, we can easily find these coefficients a, b and the c. So here, for finding this coefficient a, let us multiply the left hand side by the s. And let us evaluate the value of the expression at s is equal to 0. So here, this s in the numerator and the denominator will get cancelled out. And if we put the value of s is equal to 0, then the value of a will come out as 40. Similarly, let us find the value of this constant c. So for finding this constant c, what we will do? We will multiply the left hand side by this s plus 2 whole square, and we will evaluate the value of this expression at s is equal to minus 2. So after the multiplication, this s plus 2 whole square in the numerator and the denominator will get cancelled out. And now, if we put the value of s is equal to minus 2, then the value of c will come out as minus 80. So similarly, now let us find the value of the constant b. So for finding this constant b, once again, let us multiply the left hand side by this s plus 2 whole square, and let us differentiate this term with respect to s. And here, since it is a first order differentiation, so we will also divide it by the 1 factorial. And after the differentiation, we will evaluate the value of this expression at s is equal to minus 2. So here, this s plus 2 whole square in the numerator and the denominator will get cancelled out. And now, if we differentiate this 160 divided by s, then we will get this minus 160 divided by s square. So now, if we evaluate the value of this expression at s is equal to minus 2, then the value of b will come out as minus 40. So in this way, we got the value of the constants a, b and the c. That means now, the output voltage v of s can be written like this. And now as you can see, we can easily take the inverse Laplace transform of the each term. So we know that the inverse Laplace transform of this 1 divided by s is equal to u of t. Similarly, using the frequency shifting property, we can say that the inverse Laplace transform of this 1 divided by s plus 2 is equal to e to the power minus 2t times u of t. And likewise, we know that the inverse Laplace transform of this 1 divided by s square is equal to t times u of t. So we can say that the inverse Laplace transform of this 1 divided by s plus 2 whole square is equal to t times e to the power minus 2t times u of t. So including the coefficients, this is the inverse Laplace transform of the v of s. And if we take this 40 outside, then this is the time domain expression of the output voltage. That means this is the expression of the output voltage for the given circuit. So in this way, using the Laplace transform, we can easily find the voltage or current in the given circuit, and we can easily find the behavior of the circuit for the different types of input signals. So far, whatever examples that we have taken, in those examples, the initial conditions were 0. But in the next video, we will take few more examples where we do have some initial conditions. And for such case, we will see that how to do the transient analysis and how to find the behavior of the circuit using the Laplace transform. But I hope in this video, you understood the basic idea of doing the circuit analysis using the Laplace transform. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.